Okay, now it's time to start the next session. Okay. I'm Hiroshi Okochi from Waseda University, and I'll chair this session. At first, I would like to introduce Dr. Schnell. So, Dr. Schnell is now the Deputy Director of NOAA Global Monitoring Division, and previously the Director of Mauna Loa Observatory in Hawaii, which is famous for their observation of CO2. His research field is very diverse, ranging from biology to atmospheric chemistry. In fact, he has more than 300 original research papers. Furthermore, he discovered the biological ice nucleus and is also known as a research collaborator of Dr. Paul Crutzen, who won the Nobel Prize in Chemistry in 1988 for his research on the ozone layer destruction. And in 2007, he received the Nobel Peace Prize with the IPCC members, including the past Vice President of the USA, Mr. Al Gore. The title of his presentation is "The Air We Breathe. It is not what it used to be." Please welcome Dr. Schnell.
At the back, is the microphone picking up? Do you hear the microphone at the back? You sure? Good. Today, the students must pass this exam or they do not graduate. You've all seen a globe like this, but have you ever looked at it like this? What don't you see? Land. There's almost no land in the southern hemisphere. All the land is in the north. So that is where people live. That is where vegetation grows. And that's where pollution comes from. And you'll see today in the data. Now, if I put my hand above us here in Tokyo, this is a globe, and if I was going to draw how thick the atmosphere was, you tell me. I'm going to bring my hand down, and you stop me when I am at the top of the world's atmosphere if you had to draw it. Vote. You are all correct. If I take one hair and put it on there, 1/2 of the world's air mass is beneath that. First slide. How thick is the world's atmosphere? Very, very thin. As you can see, it is actually only half the world's air is beneath 6,000 meters. 1/2 of all the air mass is below 6,000 meters. Very thin. Now, if you burn, take 1 kilo, 1 liter of fuel and burn it, how many kilos of carbon dioxide do you form? You all know the answer, you just don't know you know the answer. Vote, basic chemistry, 3 times as much. 1 liter of fuel makes 3 kilos of carbon dioxide. Think of that. How many kilos of fuel gets burnt? Oil, coal, gasoline, you name it. How long does the CO2 stay in the atmosphere? 1 month? 1 year? 1 decade? 1 century? Closer to 1 century. To 1,000 years, the CO2 stays in the atmosphere. It only comes out permanently when it goes into the ocean. Vegetation, which grows here a lot in the spring, as you saw in the previous talk, in the springtime CO2 goes down because all of the vegetation is growing. Vegetation only grows from 2 things, carbon dioxide and water. The rest doesn't put much mass in. So in the springtime it sucks the CO2 out, in winter it comes back, and then you add a little more for pollution. And it keeps going up, as you will see. Why do we care? Carbon dioxide molecules are very small, and there's not very many of them out there. Why do we care? Because the atmosphere is heated from below, not from above. Sunlight comes down, hits the ground, changes to long-wave radiation. This radiation comes up, but it doesn't go to space because carbon dioxide and methane act like feathers in a feather bed. When you are cold at night, you put on a feather blanket. In 10 minutes you are warm because your body is putting heat up and the feathers are holding that heat. The atmosphere is doing exactly the same. There's a thin blanket that is full of carbon dioxide molecules, and they hold the heat. So if you are in a bed and you're still cold, you put an extra thick feather blanket on, you will get warmer, won't you? That's exactly what is happening in the atmosphere. But in the atmosphere, those feathers are carbon dioxide molecules, methane molecules, nitrous oxide, and a few other ones that don't really count much. So today I'm going to show you what we know about these molecules and what they're doing, where they're going, and what may happen to the Earth. Because what will we do about it? If we are starting to warm the atmosphere very rapidly, it's going to change many things. And I'm an old person, but you younger people are probably someday going to be scientists and politicians, and you are going to say, what will we do about it? Now is time to start thinking. How do we measure what is in the atmosphere? At each of these red dots, every Tuesday morning, somebody fills 2 bottles of air very carefully. It takes 1 week to learn how to fill a bottle of air. Because if you cough or have lotion on or smoke or eat too many beans, the sample is ruined. And it costs us a lot of money to send a bottle, 2 bottles, to each of these red spots every week to get filled with air. Also, we have permanent stations where people live and work to do measurements. This is the Mauna Loa Observatory in Hawaii. South Pole, right on the pole. American Samoa in the southern oceans, Trinidad Head, and of course Barrow, Alaska, where it almost is snow and no vegetation all the time. Now the worst station to work at is on top of the Greenland ice cap. It is at 3,000 meters, but very cold and very windy, and its snow is very heavy. But our scientists living there have to put up balloons, and this particular day it's minus 60 C, and it's dark. It doesn't look but the lights from the station, and they have to go outside for 2 hours to make a balloon and put it up to measure the ozone. Now the bottles these are the bottles that we put out, and they're put in pairs. And the pairs stay together. They're married. And they have to agree. When we measure one bottle and its mate, it has to agree. Or one bottle was contaminated or something was wrong. And they are shipped in pairs, 4 of them in a box, each 2 weeks they are shipped. We have 20,000 bottles moving every day around the world, coming and going. And inside these bottles, we can measure 60 different species of gas. And those gases, the concentration and the ratios tell us a lot about what is happening in the world's atmosphere. And see these tanks? You saw in the previous talk calibration tanks. Because you have free measurement, you have to calibrate. In these flasks, when we do one gas, one measurement, we calibrate twice. We do about 30 million calibrations a year. These flasks, bottles, we have 7,000 calibration bottles in our lab. Because we have to measure and then measure again, and then next year measure in the bottles or in the flasks, measure again. Some of the bottles are level because the difference in temperature between here and here can make the measurement bad. When we put out a measurement of carbon dioxide or methane, we show how we measured it and how we calibrated, and most of the world trusts us. And I see many bottles coming through. We make these standards coming from Japan, from different agencies. Occasionally here comes 2 bottles. We can tell Japanese bottles because they're taller than the Americans. They really are. They're about 1 foot taller. And we make the calibrate of gases and send them back. Next. We also measure with light aircraft. There's 12 or 14 flasks here and a little pump, and it goes into the little plane. We have 15 of these flying every week from the surface to 5,000 or 20,000 feet. That's about 7,000 meters. And we have 10 very tall towers, over 1 kilometer tall, where we measure, because this is in a forest, and when the trees grow, they suck the CO2, and then winter goes up. So now we can understand it. Next slide. This is the carbon dioxide cycle. This is the year, equator, South Pole, Mauna Loa, Hawaii. And you can see all of the places where the CO2 is measured. But you'll notice in the northern hemisphere, up and down, the southern hemisphere, nothing, because there's no vegetation. So watch as it goes up. 203, and here's the long-term record at Mauna Loa as it keeps going up. And we'll stop in about 2016 or 2014 or 15. 2016. So this is the long-term record, up and down, and then there's the Mauna Loa record, and this is where the station. Now let's see it again. Just hit it, go. Go back, and hit start. Hit. Oh, there it is. I call this the skipping rope. Remember when you were a child, you played the skipping rope? One person held it steady and the other one moved it up and down. But see, that is how mankind, this is all because we are burning fossil fuel. And look at it, isn't it interesting? This is Mauna Loa again, equator, North Pole, South Pole. It's all driven by the Northern Hemisphere. And the years going very fast. Next slide. So you put this all together. This is the Mauna Loa curve. Keeps going up and up and up. But in the ocean, near Hawaii, we also measured the CO2 in the ocean water, because all of the CO2 eventually has to go into the ocean. There's no other place for it. But as it's doing that, it changes the pH. And it's getting more acidic every year. As it's getting more acidic, it is starting to change the growth in the ocean. The plankton, the mollusks are all slowly being affected. What is going to happen when it gets much, much, much more acidic? This is really pretty scary for the food source. Next slide. If you put all of the CO2 measurements from that map you saw, you get a three-dimensional picture. So here's the equator, comes straight up from the equator. There's the equator right there. This is the northern hemisphere, 0 to 90 degrees north and 0 to 90 degrees south. So remember, you've got to come straight up. So that's the north or south pole, and that's the north pole. But look how the Earth inhales in the spring, sucks the CO2 out, then in the fall, up, every year. But also see, it's all in the northern hemisphere, because that's where the people are, that's where the vegetation is, that's where the burning of the fossil fuel is. The southern hemisphere is just an echo, hardly anything happening down there. Next slide. Methane, the second most important greenhouse gas. You'll notice in 1980s it was going up steady at 13.5 parts per billion every year. Then it started leveling out, and then it leveled out. But in there was a big peak right here, right there. There was another peak here, and now another peak growth here. This is the growth rate. So there were periods when the growth rate went to almost zero. There's periods when it went below zero. But from our flask measurements, we can look at the isotopes of the methane. So we can tell, is it coming from agriculture? Is it coming from fossil fuels? And we can look at the different ratios and tell you which oil field it came from. And when the USSR collapsed, methane went up. Let me ask you a question. In the 1980s and 90s, which country in the world produced the most methane or natural gas? Russia. Which country produced the most oil? Not Saudi Arabia, not Venezuela, Russia. Which country did they ship their methane to? The European Union. Their pipelines were big enough that you could walk inside them. But when communism fell, they couldn't fix them anymore. They started leaking, and the whole world was seeing the effect of the methane. They fixed the pipelines, and the methane growth went down to essentially zero. And then in 1997, 98, the ruble collapsed. The economy in Russia collapsed, ruble was worth a certain amount one night, the next day it was divided by 10. They couldn't fix their pipelines and it leaked again. They got them fixed. Now, in the last few years, methane has been going up. Everybody looked at Russia. No, it's not coming from Russia. It's not coming from oil drilling in the US. It's not coming from Saudi Arabia. It's coming from the Amazon. How do we know that? Because we have stations and we can see the rise. Why is it coming from the Amazon? Because the Amazon has the largest tropical forests in the world and their rainfall is increasing. And in the Amazon, during the rainy season, becomes a big ocean. Even where the forests are, it's a little bit above sea level, but the water is up to 6 to 8 feet in the trees. And that is causing more anaerobic decay because the leaves are underwater. So contrary to what people think, it's coming from Amazon. And we can tell that also because of the isotopes. Now we see that it's coming from decayed vegetation, not from old natural gas. In the US, many people are blaming the oil and gas companies because they're doing so much drilling and fracking and leaking, but that's not the case. Next. If you look at all of the methane in the same way as we looked at CO2, look how interesting it is. It's all in the northern hemisphere again, because that's where people are, that's where vegetation is, that's where decay basically is, except for the Amazon. But Amazon, some of it's in the northern hemisphere. The equator goes through the Amazon. But again, you can see the annual cycle. Some of this is also driven by the OH, which destroys the methane. But for the most part, it's sources. And there's where Japan fits right in there. Next slide. So, you've all heard about permafrost in Russia. There's a lot of methane frozen in the permafrost. As much methane in Russia in the permafrost as has come out into the atmosphere in history times. Huge amount of methane. And if the permafrost warms, what's going to happen? Methane is going to go up. And many people think that it is melting already. But we have two stations. One in Tixi, Russia, and one in Chersky. And they're right on the Arctic Ocean. To get to Chersky is a 3-day trip. To get to Tixi is a 4-day trip. Because you have to fly to Moscow, then you fly to Yakutsk, then you fly to Kornu, and then you fly to Tixi. The same. It's very long and expensive to go there. I've only been to each once. No, Chersky twice, Chersky, but I'll probably never get there again. We are measuring. Next slide. How do you measure methane in Russia with very great difficulty? This is on the tundra, and this is about 100 kilometers from any civilization. So we got an old building, and you see this is a troop carrier that can go on muskeg, and pulled this all the way out there. The Russians built a nice tower. We put our equipment in a very thick insulated box, and we run an extension cord 17 kilometers to a cabin where a hunter lives, and he puts gasoline in the generator. And he's paid to just do that, to keep this going. We have not seen any leaking methane from the permafrost yet. So we are still safe. Next slide. Oh, somehow we've cut off the bottom, but don't worry. You get the idea. Carbon dioxide, nitrous oxide, and methane. Look here. The Industrial Revolution, that's how much we've changed the atmosphere since 1850. Isn't that amazing? And we know this because we look inside ice cores. You can take an ice core, slice it, melt it in a vacuum, take off the gas, and there you know. The error bar is large, but if you do enough of them, you get a pretty steady picture. 285 parts per million CO2, and then all of a sudden, now we're up to 402, 410. It's just amazing. And look at methane, it's just going up. Nitrous oxide, not so fast. Nitrous oxide comes from something we all do to help agriculture. When you take methane or ammonia fertilizers, you put them in the ground, the plant takes the energy, but it's got to put something out, doesn't it? N2O, nitrous oxide. So the green revolution is eventually going to help change the climate. So it's like a big water bed. In Japan you have water beds. A bed's made of water. One person rolls over, the other one moves, and vice versa. That's how the atmosphere is. Sometimes something seems good somewhere, but it affects somewhere else, and that's exactly what's happening here. If you take all of the gases that have gone into the atmosphere over time, and if you set, arbitrarily we set 1990 as 1, and that comes up here, and we come across, that's 1. And then you take the amount of feathers, methane, carbon dioxide, nitrous oxide, that have been put into the atmosphere, into this blanket. We have now added 40% more feathers to the atmospheric blanket around the Earth. That is basic physics. You can argue politics, religion, economics, but you cannot argue physics. We have increased the blanket across the Earth. It's going to get warm, and it's going to get warm for at least the next 100 to 1,000 years, because that's how long it's going to take for the CO2 to go out of the atmosphere. A very sobering graph. Even if we cut down methane and all the other gases, we are still going to put out CO2 for a long time. Next slide. I'm watching my time. What is it doing to the atmosphere? Temperature. Going up now. Here's the years. 1950s it started. But between the 1950s and 2000, all of a sudden, temperature really started to go up steadily. Average sea level is changing, not by much, but it's steady. And it's changing for 2 things. When you warm water up, what does it do? It expands. We're warming the oceans. Plus, we're melting a lot of Greenland and a lot of Antarctica, so the ice is getting smaller. Some of the glaciers are disappearing. The glaciers don't raise sea level much compared to Antarctica and Greenland, where all of the ice is. And the northern hemisphere snow cover is going down. There's less snow staying on the Earth, and what that has 2 effects. It tells you that the snow is melting because it's warmer, but also when the snow goes away, it doesn't reflect heat, so now vegetation and ice going away, the seawater in the Arctic holds more heat. So it's a feedback that's going to probably get faster and faster and faster. It's a self-feeding. For those of you making notes, I will leave all these pictures plus a bunch more, and you can get them if you want from the organizer. Next slide. So what do we see? This is the Arctic, Greenland, US, Russia. In 1979, the average ice edge in summer was there. Today, it's here. And this graph shows you how it's going down. And the poor bears, they live on the ice. And the ice is disappearing. the bears are getting thinner and a lot of them are dying because they have to be on ice to eat seals. And if the ice gets smaller, there's more bears competing for less seals because the seals aren't coming up. Self-defeating. One day, someday, there's going to be no ice in the Arctic in the summer, and a lot of the polar bears will be gone. Next slide. Now let's look at some other things that should be of interest to you. This is a satellite picture of aerosols or air pollution. Here's China, here's Japan, Korea, and NOAA is involved with 3 stations, 2 in Korea, Anmyeongdo and Gosan, measuring aerosols, and with George Lin in Taiwan at the Lulin station. And as you know, the wind blows which direction, generally? A lot of your wind comes from the west or northwest to bring whatever is in China to Japan. And we measure at these, and we'll show you some interesting slide next. We also have stations around the world, cooperative stations, where we measure the dust and the aerosol pollution. It's called the Federated Aerosol Network. We actually have stations in China. The biggest one is at Hualiguang, but we do most of our work at Anmyeongdo and Gosan in Korea and Lulin in China, or Taiwan, and the wind comes this way. And these stations have all exactly the same instruments. We show the different governments what to buy, we help them calibrate, and all of the data comes to us in Boulder, and every morning one scientist goes in and looks at all the stations and checks their data. And we can actually turn instruments on and off, adjust, or send an email and say, you must put 1 quart of water in instrument 2 because it's not measuring carbon dioxide or condensation nuclei. We can do that. And this way, all of these instruments are measuring the same thing, and we monitor them and make sure that the data is accurate because we calibrate a lot of these stations. We do the ones in Korea 3 times a year, Lulin once a year, Hualiguang once a year, where we send people there and work with them at the station. Next slide. So what do we get from this? You may have seen this picture before. Here's Korea, China, Japan. You know what a COSA is, don't you? Well, look here. The satellite sees this line of dust, and the winds are blowing this way, right here. It's a frontal system, and every few weeks in spring and winter, you get these cold fronts coming out of China. This particular one, look here. See the air pollution? The bluish white, that's air pollution that was once in China. I'm sure many of you have been to China, and in Beijing and industrial areas, sometimes you cannot see across the road. A cold front comes through, just like flushing a toilet, all of the pollution goes out to Korea and Japan. And first the pollution comes by, and then you get a mix of dust, and then you get very nice clean air behind it. Beautiful, clean air. Now, look at this. Number 1, 2, and 3. Remember where that is. Number 1 is in this pollution. Number 2 is a mix between dust and pollution, and number 3 is right in the dust layer. Next slide. Here's filters. There's filter number 1. That's the air pollution that's coming in front of the cold front that has passed out of China, across Japan, and goes to Mauna Loa Observatory. Mauna Loa Observatory regularly gets polluted from China like this. Boom, boom, boom. Because, and then where it's mixed, you can see a yellow dust and the pollution, and then after right where the dust storm comes, and if there was another filter here, it would be pure white, because the air is very nice. And this keeps repeating. Next slide. Now, a new actor in the game is India. India is really starting to generate up its economy. And they have, I think, 300 million people without electricity. In the next 10 years, everybody in India will have electricity. That is very good, because once you've got electricity, you can have refrigeration. Now a person doesn't have to go out every day and buy fresh food, they can store it. Electricity, you have lights at night and television, internet. But where does the electricity come from? Burning coal. In India, they're putting new coal power plants in continuously. And they burn very poor brown coal. And on any winter day, if you look at satellite, look here. See this haze? See the haze coming out here? This is highland here. This is the Himalaya mountains. The pollution in winter and spring flows in cold air exactly as water does. If you know anything about water, you can just do pollution, because it just follows the valleys down the hill and out it goes. Here's the pollution, comes across, follows the rivers. Look at all the rivers across Bangladesh and out into the Indian Ocean, and then it's picked up and it starts coming. So even if China, which is really working hard to cut their pollution, it will be made up and more by what's coming out of India. And you can't blame them, because they want the electricity, they want the benefits of electricity, and who are we to say you cannot do that? But it's going to affect the world. Next. Now let's have a different story. You've all heard about the Antarctic ozone hole. In fact, it was a Japanese that discovered that, but he didn't publish it at the right time. Remember, around Antarctica, fluorocarbons collect in the winter. There's no sunlight. Then in the spring, as soon as the sun hits those fluorocarbons, it's the biggest chemical reaction on Earth. It's bigger than all of Antarctica. It starts just like if you could hear it, it'd be like 1,000 freight trains.